Okay, we are on to section 2.5, acceleration. All right. If the velocity of a particle changes with time, the particle is accelerating. Example, magnitude of a car's velocity increases when you step on the gas and decreases when you apply brakes. Both of these actions result in an acceleration of the car. What is another component of your car that causes acceleration? Think about it. So you have the accelerator pedal, you have the brake pedal. What other object in the car causes an acceleration? The answer is the steering wheel. Even though you're going, even if you're going the same speed around a curve, your steering wheel is causing you to change your direction. And from our definition of a vector, having a magnitude and direction, changing direction is an acceleration. Okay, so you need to quantify your acceleration. Suppose the object modeled as a particle moving along the x-axis has an initial velocity vx initial, vxi, at time ti, t initial, at position A, and final velocity vxf, vx final, at time t final, at position B. This is figure A in the left-hand side. The red-brown curve, figure B, shows how the velocity varies with time. The average acceleration, AX, average of a particle defined as the change in velocity, delta Vx, divided by time interval, delta t, during which that change occurs, is shown here. Average acceleration is the change in velocity over the change in time. Vx final minus Vx initial, divided by t final minus t initial. Okay. When motion is in one dimension, use plus and minus signs to indicate the direction of the acceleration. Note, dimensions of velocity are L and T, L divided by T, and dimension of time is T. So the acceleration has dimensions of length divided by time squared, or L over T squared. Give an example of miles per hour per second. I mean, it sounds funny to have time squared, but if you think of, well, if you have an acceleration of 5 miles per hour every second, in the first second you're going 5 miles an hour, the second second you're going 10 miles an hour, and the third second you're going 15 miles per hour. 5 miles per hour per second. And that ends up being a time versus time. So don't let the time squared intimidate you. The SI unit of acceleration is meters per second squared, or meters per second per second. Example, suppose the object has acceleration of plus 2 meters per second squared, plus 2 meters per second per second. The object has a velocity along a straight line and is increasing by 2 meters per second during every time interval of 1 second, 2 meters per second per second. If the object starts from rest, it moves at a velocity of 2 meters per second after 1 second and 4 meters per second after 2 seconds, and so on. Okay. Now, when your friend sped up from the traffic light in your opening storyline, if you read the storyline, you found that the time intervals between poles on the side of the road decreased. That is that they came together in shorter time intervals because you're going faster. Is that result consistent with your expectation? Each new displacement between the poles is undertaken at a higher speed, so the time intervals between the poles become smaller. Sometimes the value of average acceleration may be different over different time intervals. Instantaneous acceleration is the limit of average acceleration as delta t approaches 0. Analogous to the definition of instantaneous velocity. Figure A, the image, imagine a point A is brought closer to point B. Take the limit delta Vx divided by delta t as delta t approaches 0. You get the instantaneous acceleration at point B. So A is the limit as delta t approaches 0, or delta Vx over delta t. which is dvx over dt in calculus notation. Instantaneous acceleration is the derivative of the velocity with respect to time. By definition, it is the slope of the velocity versus time graph. I'm surprised it doesn't say it here, but it's also the second derivative of the position versus time graph. The slope of the green line, figure B, is the instantaneous acceleration at point B. Note the graph is velocity versus time graph, not the position versus time graph. Velocity of a moving particle equals the slope at the point on the particle's x versus t graph, the position versus time graph. Acceleration of the particle is the slope at a point on the particle's velocity versus time graph. Interpret the derivative of velocity with respect to time as the time rate of change of velocity. If a sub x is positive, then the acceleration is in the plus x direction. If ax is negative, then the acceleration is in the negative x direction. Okay, let's look at the figure. It illustrates how acceleration versus time graph related to velocity versus time graph. The acceleration at any time is equal to the slope of the velocity, equals the slope of the velocity versus time graph at that time. Positive values of acceleration correspond to points where the velocity is increasing in the positive x direction. The acceleration reaches a maximum at time ta. That is, the slope of the velocity time graph is maximum. That's when the slope at ta is a maximum. Acceleration goes to zero at time tb, where the velocity is a maximum. When the slope of vx versus t graph is equal to zero. In other words, that's the velocity has been increasing. All of a sudden, it comes to stop, and it's going to start decreasing. Imagine throwing a ball up in the air. The velocity, you start at the initial velocity, it slows down, and then comes back down, increasing in the negative direction. Okay, acceleration is negative when the velocity decreasing in the positive x direction reaches its most negative value at time equals t sub c. Okay. It's time for a quick quiz. Let's see. Make a velocity versus time graph for the car in the figure. Suppose the speed limit for the road on which the car is driving is 30 kilometers per hour. True or false? The car exceeds the speed limit at some time within the interval 0 to 50 seconds. Well, let's see. This Vx versus t graph shows that the maximum speed is about 5 meters per second, which is the equivalent of 18 kilometers per hour, which is about 11 miles per hour. So the driver was not speeding. Okay. We are still discussing acceleration. The force on an object is proportional to the acceleration of the object. We'll get into this in more detail when we get to Newton's laws of motion. For straight line motion, the direction of velocity of an object and the direction of the acceleration are related. When the object's velocity and acceleration are in the same direction, the object is speeding up. When the object's velocity and acceleration are in opposite directions, the object is slowing down. Velocity and acceleration in the same direction, the object is speeding up. Velocity and acceleration in the opposite direction, the object is slowing down. Relate the acceleration of an object to the total force exerted on the object. Force is proportional to acceleration. Well, again, we'll get to that when we get to Newton's laws. Acceleration is caused by a force. The force and acceleration are both vectors, and they're vectors in the same direction. Think about signs of velocity and acceleration by imagining force applied to an object and causing it to accelerate. Assume the velocity and acceleration are in the same direction. It corresponds to the object that experiences a force acting in the same direction as the velocity. The object speeds up. Suppose the velocity and acceleration are in opposite directions, and the object moves in some direction and experiences force acting in the opposite direction, so the object slows down. Useful to equate direction of acceleration to direction of force. It's easier to think about what effect a force will have on an object. Force can either make something speed up, or the resistive force will make it slow down. Time for a quick quiz. If a car is traveling eastward and slowing down, what is the direction of the force on the car that causes it to slow down? Is it eastward? If the car is traveling eastward and the force were eastward, it should speed up. If the direction of the car is eastward, but the force is in the opposite direction, westward, which should cause it to slow down. So the answer is westward. The direction of the force on the car is westward. Okay. Acceleration. Use acceleration to mean instantaneous acceleration. For average acceleration, always say average. Since delta v equals delta x over delta t, acceleration can also be written down as shown. In one-dimensional motion, the acceleration of a particle is the first derivative of the velocity and the second derivative of the particle's position x with respect to time. So acceleration is the first derivative of the velocity with respect to time and the second derivative of the position versus time. Okay. The position of an object moving along the x-axis with time, as in the figure, varies. Okay, I'm sorry. The position of an object moving along the x-axis varies with time, as in the figure. Graph the velocity versus time and the acceleration versus time for the object. Okay. The velocity at any instant is the slope of the tangent to the x versus t graph at that instant. So between t equals 0 and t equals t sub a, the slope of the x versus t graph increases uniformly. So the velocity increases linearly as shown here. Between ta and tb, the slope of the x versus t graph is constant, so the velocity remains constant. Notice how it's flat. The velocity is flat between ta and tb. Between tb and td, the slope of the x versus t graph decreases, so that the value of the velocity in the vx versus t graph decreases. The velocity is going down. And at td, the slope of the x versus t graph is 0. So the velocity is 0 at that instant. Between TD and TE, the slope of the x versus t graph, and therefore the velocity, are negative and decrease uniformly in this interval. In the interval TE to TF, the slope of the x versus t graph is still negative, and at TF it goes to 0. Finally, at TF, the slope of the x versus t graph is 0, meaning the object is at rest for t greater than TF. All right, now let's add acceleration to this graph. The acceleration at any instant is the slope of the tangent to the Vx versus t graph at that instant. The graph of acceleration versus time for this object is shown in the bottom figure. The acceleration is constant and positive between 0 and t sub a, where the slope of the Vx versus t graph is positive. It is 0 between t and tb for t greater than tf, because the slope of the Vx versus t graph is 0 at these times. It is negative between TB and TE because the slope of the Vx versus t graph is negative during this interval. Between TE and TF, the acceleration is positive like it is between 0 and TA, but higher in value because the slope of the Vx versus t graph is steeper. Between TF and TE, yes. Okay. Notice that the sudden changes in acceleration are unphysical. Such instantaneous changes cannot occur, they don't occur naturally. Okay, let's look at some examples. The velocity of a particle moving along the x-axis varies according to the expression Vx equals 40 minus 5t squared, where Vx is in meters per second and t is in seconds. Okay, find the average acceleration in the time interval t equals 0 to t equals 2 seconds. Conceptualize, oops, there we go, conceptualize. Think about what the particle is doing from the mathematical representation. Is it moving at t equals 0? In which direction? Does it speed up or slow down? Shown is a Vx versus t graph that was created from the velocity versus time expression given in the problem statement. Because the slope of the entire Vx versus t curve is negative, we expect the acceleration to be negative. Categorize. The solution to the problem does not require either of the analysis models we have developed so far and can be solved with simple mathematics. Therefore, we categorize the problem as a substitution problem. Find the velocities at t initial, which is equal to TA which is equal to 0, and t final, which is equal to TB, which is equal to 2 seconds. By substituting these values of t into the expression for the velocity, the 0 and the 2, we get the velocity 40 meters per second for Vx equal to A and 20 meters per second for Vx equal to B. Find the average acceleration in the specified time, TB to TA, and the acceleration, the average acceleration is Vx final minus Vx initial divided by T final minus T initial. So it's 20 meters per second minus 40 meters per second divided by 2 seconds. And so you end up with a minus 20 divided by 2, and it's minus 10 meters per second squared. Okay, the negative sign is consistent with our expectations. The average acceleration represented by the slope of the blue line joining the initial and final points on the velocity time graph is negative. Okay, determine the acceleration at t equals 2 seconds. Knowing that the initial velocity at any time t is Vx initial equals 40 minus 5t squared, find the velocity at any later time t plus delta t. Okay, there it is, Vx 40, we're just substituting t plus delta t into the initial equation. Find the change in velocity over the time interval delta t. Let's see. Okay. To find the acceleration at any time t, divide this expression by delta t and take the limit of the result as delta t approaches 0. Ax equals the limit as delta t approaches 0. Delta Vx over delta t is the limit as delta t approaches 0 of minus 10t minus 5 delta V equals minus 10t. Substitute t equals 2 seconds. and you get your answer of 20 meters per second squared. Because the velocity of the particle is positive and the acceleration is negative at this instant, the particle is slowing down. Notice that the answers to parts A and B are different. The average acceleration in part A is the slope of the blue line in the graph connecting the points A and B. The instantaneous acceleration in part B is the slope of the green line tangent to the curve at point B, that green line right there. Notice also that the acceleration is not constant in this example. Situations involving constant acceleration are treated in section 2.6. Most of the time we will deal with constant accelerations. We will discuss varying accelerations. We'll learn that it's area under the curve. This ends our discussion of section 2.5. The next section we will discuss will be section 2.6, motion diagrams.